Okay, we're going to talk about how solar cells work. So many cells make up a single solar panel. So we're going to zoom in and talk about how the cells work. There are three elements that make solar cells work. The first is silicon, which is obviously solid at room temperature, and it has a lattice structure. It's a crystal that is actually the same geometric structure as diamond, but the nuclei of the silicon atoms are a little farther apart than in diamond, which is why silicon is not quite as tough as diamond at room temperature. So silicon is the first one. Then there's phosphorus, and phosphorus is important for reasons we'll talk about in a minute. And boron. Boron's the last element involved in all this. We'll talk about each of these in turn. So silicon. Silicon is a very symmetric molecule. It has a bunch of electrons. Here's the nucleus in the middle, the electrons on the outside, but only really, oversimplifying a little bit, it's four outermost electrons, the valence electrons, 1, 2, 3, 4, take part in bonding with other atoms. So that's going to come into play in a second. Those are the four atoms that bond with nearby silicon atoms. Phosphorus is pretty similar, but instead it has 5 valence electrons in the outermost shell. And this means that when you inject phosphorus into silicon, there's this extra atom or electron that doesn't bond and just floats around the crystal lattice kind of free. And finally, boron has only 3 valence electrons, and that means that there's sort of an open spot where if you added another electron, it would bond with the silicon around it. So what does that look like? Here's a quick sketch. The silicon here forms covalent bonds using those valence electrons 1, 2, 3, 4, and then they each share, basically they share an electron between each of them. So this silicon atom in the middle is creating a bond here, 1, 2, 3, 4, and then all the silicon atoms around it also share a bond. You've got your silicon lattice. It's a crystalline lattice in which each silicon atom, here's an example, has 4 bonds. It's pretty simple. They're in these kind of Y shapes. And each silicon atom is bound in this lattice to 4 other silicon atoms. So it looks something like this in this lattice structure. With the phosphorus, you've got this extra electron that's only really weakly still connected because those other bonds have formed with its 4 other valence electrons to the surrounding silicon. So this final electron is really weakly held, and even at like room temperature, this tends to float around and like leave the phosphorus. Finally, boron, there's just an empty spot right there where an electron could kind of slot in, and that's going to be important in a second. Okay, so how does this make solar cells work? Solar cells are basically a sandwich, and you've got 2 pieces of silicon, and on the top part of the silicon you inject phosphorus atoms. Not very many. The actual concentration of phosphorus in the silicon lattice, the number of phosphorus atoms that are sitting in the silicon is actually quite low, but you've got some phosphorus in this top part. And in the bottom part, you've got the boron-doped silicon. So you've injected a little bit of boron, again, a small amount, into the silicon lattice. Just to kind of represent that, I've got these 2 little stickers. So there's kind of what the top might look like hypothetically, and then the bottom might look something like this. Again, this is an oversimplification. This is obviously 3-dimensional. The lattice structure is a 3D object, but in 2 dimensions it might look something like this. Now, to explain how the solar panel actually works, we're going to abstract away, and we're actually going to just remove the silicon from the picture here. It's still there. It's still there, but we're just only going to show the phosphorus and the boron atoms because they're sort of doing a lot of the important work here. But just remember that the silicon lattice is still there. We're just not going to show it to make the drawing sort of easier to follow. So I'm going to take this away. One final thing, the sun is going to be coming from this direction, from the top. Okay, so here's a simpler drawing. We've just got our, our phosphorus that's embedded in the silicon, which again is there, but I'm just not showing it. And then the boron on the bottom is embedded in the silicon lattice. So what's happening here? If we go back to our representations of our atoms, we'll remember that the silicon atom is sort of symmetrical, but the phosphorus atoms have these extra electrons that are floating around, which we're going to represent with these little red dots that I cut out from an Economist magazine. And those are going to represent the extra electrons that are floating around in the phosphorus region at the beginning. And just to underscore this, there's no sunlight yet. This is just the solar cell we've assembled. It's in the dark, and there's no wires attached. So the wires will eventually attach here and here on either side, and those will be connected to like a light bulb over here. So we have a complete circuit going from the top to our light bulb, then out of the light bulb, another wire will come down and attach to the boron. So we've got those extra electrons because the phosphorus had that extra electron. And in the bottom, I'm going to represent the little spots where the electrons could go, because we have the boron atom, when it binds to the silicon lattice, has that extra open spot. I'm going to represent those with these little holes. In the silicon sort of like semiconductor and solar cell literature, these are referred to as holes, which is just the absence of an electron in the silicon lattice where there could be one. Okay, so what happens next? This is where things get kind of interesting. The electrons start to migrate down because basically a diffusion gradient. So, electrons repel each other, these free electrons. They don't want to be next to each other necessarily. And they could take up space over here. Nature sort of abhors a vacuum, so they're going to start migrating over here like that. And they're going to fill in some of these holes in the boron that's close to the junction or the boundary where these two layers meet. And they're not going to make it to the bottom because they'll sort of get caught by the boron holes that are near the junction. They're not going to make it like all the way down here. As that's happening, an electric field is actually created. So how does that happen? Keep in mind that the phosphorus atoms and the boron atoms are trapped in the silicon lattice. So they're not actually moving anywhere. It's just the electrons that are moving. So when the electrons move down from the phosphorus area in here to the boron, these phosphorus atoms, keep in mind phosphorus, if we go back to our little visual aid, phosphorus has 15 protons and 15 electrons. But these phosphorus atoms have lost an electron. They've gone down here. Before, when they were all just up here, the net charge, the net electric charge of this region was neutral because there were an equal number of protons and electrons in the region in general. Maybe not like locally right next to every phosphorus atom, but overall, on average, there was an equal number of charges. Now, in this area, in the phosphorus area near the boundary, these phosphorus atoms are going to have a positive charge. So this area is going to be positively charged. And again, that's because those phosphorus atoms, now they've sort of locally, their electrons have jumped over to the other side, and there are more protons, more positive charges than electrons in this area. Meanwhile, the boron has, normally it has 5 protons and 5 electrons. So 1, 2, 3, 4, 5. Remember, that's including the ones in the inner rings, not just the valence electrons. But we've gained an electron. So one of those holes that we previously talked about in the structure, if we look here, I'm just going to show that. This hole is being filled in by the electrons that moved over. The upshot of that is now the boron, which was neutrally charged, because they have an extra electron, now this is negatively charged in this specific region near the boundary. These down here in what's called the bulk area, just down close to the end and up here closer to the top, that might be sort of still neutrally charged because there's not electron movement on net necessarily in this area and near the bottom. But near the boundary, we now have a positive charge and a negative charge. And the upshot of that is that we're going to have an electric field. And that electric field is going to repel more of these electrons from the phosphorus side from coming over, because they'll want to go down, maybe because of diffusion. But then the electrons that are already over here in the boron, that negative charge, the electric field, will repel them back up. So they'll be up here. Similarly, you might wonder, well, why don't these just go further down? And partly that's because they're, again, the electric field is pushing those electrons up. It's pushing them up. And you could also think of it as they're, attracted to the positive charge on this phosphorus side, just on the other side of the boundary. This little area around the boundary, when this electric field is created, in the literature, this is referred to as the depletion region. You don't really need to know that, but if you happen to see that, that's what they're referring to. Okay, so there's sort of an equilibrium that is created when the diffusion force that's pushing electrons kind of down towards the boron is equilibrated with the electric field force that's pushing those electrons back up. So you reach an equilibrium, and now you've sort of got this electric field that's formed in the middle. And that just happens because we put the phosphorus-doped silicon next to the boron-doped silicon. We haven't connected any wires yet. We haven't introduced sunlight yet. That's just a physical property of having these two pieces of this sandwich next to each other. Okay, so now what happens when we connect some wires and we turn on, attach those wires to a light bulb over here, and then the wire comes back around to the side. So when the sunlight hits the depletion region, hits this middle area near the junction, the electrons get, and this could happen with the boron atom's electrons, or this could happen with the silicon area's electrons, because remember, this is all in a silicon lattice. So some electrons near the junction are going to get hit by the sunlight, which is just energy. They're going to hit by photons from the sun, so a form of energy. That's going to split off some of these electrons, which I'm just going to show with that. And they're going to go this way. They're going to go up. Now, why are they going to go up? It's because the electric field is going to push those electrons up. They're going to be attracted, you can think of it this way, to the positive side, because electrons are negative, they have a negative charge. So they're going to get pushed up. Now, you might be wondering, well, why wouldn't they just stop, if they're attracted to the phosphorus side, why wouldn't they just stop here in the phosphorus that's near the region, like in this area that is sort of devoid of electrons? And the answer is because, remember, these phosphorus atoms, they're full up on connections, sort of covalently bonded to the silicon, as we discussed earlier. So there's not really a natural place for those electrons to slot in. So this is almost like they're being accelerated up, as if you were to push a car that was in neutral and then kind of let go. So they're going to actually just go, they're going to slide right past the little middle phosphorus region there, and they're just going to go up. And that's going to keep happening as long as sunlight is hitting the region. I'll show that with this one. So there's another electron, and it's just going to go up. And you might be noticing what's happening here is that electrons are building near the top of the solar cell in this phosphorus bulk region at the top. So sunlight is continuing hitting, and then When you attach a wire, so we can draw that on here. Let's just say we, got a wire here like that. And then that just goes off screen to a light bulb, we'll say. And then from the light bulb, it connects at the bottom again, just like that. So what's going to happen? There's now a diffusion gradient that's forming. So these electrons are going to want to get away from each other. They're going to go this way. They're going to go out into the wire because they don't want to be next to each other. And the electric field is pushing them up, just away from this area. And that's continuously happening. So they'll go to the light bulb. They're flowing this way. They go to light bulb. And remember, the movement of electrons is just another way of saying an electric current. So we've created an electric current because the sunlight is hitting this depletion region. The electrons are being propelled via the electric field this way. Now we've got movement of electrons, which is electricity. So they go, they turn on the light bulb, they come back, and then, oh, there's the place they want to be. They want to be in these little holes. And as that's happening, you might wonder, well, why did they go from the holes, the open spots in the boron silicon lattice down here? Why would they go up again? And the reason is that this process is continuously happening. So you've got, these are going to get broken loose and they'll go up, and then more spots will fill here. And there'll be a diffusion gradient that goes in combination with the electric field, pushing this way. These electrons will migrate up again through just, up towards the top. And that will keep happening as electrons come from the top and go around and then come back up here and fill in these holes at the bottom. So it's just a continuous process. And that's pretty much how solar cells work. I'll talk about how they're made in a second, because it's not like they literally just take two separate pieces of silicon and then smash them together. You basically add a bunch of heat and then put a phosphorus on the top and boron on the bottom, and then the phosphorus actually sort of worms its way into the silicon, and same with the boron. How that happens, we can talk about in a second. But fundamentally, that is how solar cells work.